We'll use the photonic crystal cavity resonator structure again for this demonstration. The photonic crystal cavity is made of a Z-normal dielectric slab with a pattern of holes etched into the slab forming the cavity. We will add Z-normal movie monitors in the slab to create movies of the electric field intensity and the Z component of the electric fields. The movies will show the initial source pulse injected by the dipole source and the resonant fields in the cavity. Start by adding a movie monitor from the Monitor's drop-down menu. Edit the monitor. Under the field component, electric field intensity is selected, and this is what will be recorded in the movie that will be generated. The T, M, and TE field component options are used for 2D simulations, so these settings don't apply for our 3D simulation. We will use the default resolution and scale. The Draw Structure Outline setting is selected, so I'll be able to see the outlines of the holes of the photonic crystal in the movie. Under the Geometry tab, make sure that the monitor is centered and set the X and Y spans of the monitor to 2.5 microns to match the span of the simulation region. Finally, I want the movie file name to indicate that the movie is showing the electric field intensity, so I'll set the name to E-intensity movie. Next, I'll duplicate the monitor to create another movie where I'll just record the Z component of the electric field. Edit the monitor and set the field component to EZ. I'll set the name of the monitor to EZ movie. Click OK to accept the settings. Run the simulation. After the simulation is complete, check your current working directory, which is my desktop in this case, and I can see two movies. First, I'll play the movie of the electric field intensity. I can see the initial source pulse, followed by resonant field pulses. The field intensity at the beginning of the movie is a bit saturated, which can be seen by the uniform red area of the fields. So if I wanted to reduce the saturation, I could set the scale setting of the movie monitor to a larger number and rerun the simulation. However, keeping the scale has the advantage of allowing me to more clearly see the fainter radiation of light escaping the cavity later on in the movie. Next, I'll play the movie showing the EZ field component of the fields. Here, because the fields have positive and negative values, the color scale goes from blue to red for the lowest and highest field values. Green in this movie indicates the center of the color scale, corresponding to the field amplitude of 0. Since there were only positive values in the field intensity movie, blue indicated an amplitude of 0 in the previous movie. Because the file name of the movie file that's generated is determined by the simulation file name and monitor name, make sure not to have two monitors with the same name, and rename existing movie files before rerunning the simulation if you want to keep the previous file from being overwritten. The resolution of the movie is one of the monitor settings, but remember that the resolution of the field data is still limited by the simulation mesh. So if you want to get smoother fields in the final movie, you may need to use a finer simulation mesh. If you find that the fields in the generated movie are saturated, or they're too faint to make out, adjust the scale setting of the movie monitor and rerun the simulation. The .mpeg movie file can be played using almost any video player software. However, some video players will allow you to play the partial movie while the simulation is still running, so you can preview what's happening in the simulation before it completes, whereas others only allow you to play the movie once the full movie file has been written. The movie monitor does cause the simulation execution time to take longer, so it's best to disable the movie monitor if you're running a parameter sweep and you don't plan on using the movies generated from each simulation file, and only enable the monitor when needed. Finally, the movie monitor generates a movie of the fields in the time domain, but it's also possible to generate a movie to show the steady-state response at a particular frequency. and this can be done using the CW Movie with MATLAB analysis group in the object library. This uses the frequency domain monitor and exports the monitor data to MATLAB where a movie can be generated. For more details, see the Making a CW Movie page linked below.